Hello, today we're going to talk about the molecular structure of acids and bases. So let's review really quick conjugate pairs. When you have something like acetic acid, it's a weak acid, HC2H3O2, in water, it's going to form our conjugate base C2H3O2 and hydronium. Okay, don't forget that hydronium and hydrogen ions can be used interchangeably, but this is the full equation of what happens. So this is our acid, this is our conjugate base. Okay, the Ka for that reaction is 1.8 times 10 to the negative 5. Okay, that is our acid dissociation constant. Let's do another one. If we have HF reacting in water, it's another weak acid. It's going to form that conjugate base fluoride ions and hydronium ions. Its Ka is 6.6 times 10 to the negative 4. So just by comparing those Ka values, I know that HF is a stronger acid than acetic acid. All right. Let me go ahead and label this as the acid. This is the conjugate base. So HF is a stronger acid. I'm going to write this down so we have it. HF is more acidic than HC2H3O2. All right. Now, based on the strength of the acid, we can predict the strength of the conjugate base. So, the stronger the acid, the weaker the conjugate base. So I'm going to write conjugate base. Our conjugate base of fluorine, HF is fluoride, and our conjugate base of the acetic acid is acetate. So it must be in reverse, right? Because HF is the stronger acid, fluoride is a weaker conjugate base. Because acetic acid is a weaker acid, acetate is a stronger conjugate base. So that's how you can compare it. They could also ask you which side of the reaction is favored in this. For the most part, we're going to see very little of the products being formed, but they could ask you to compare. So like in this first reaction, we have the acetic acid, the water's acting as a base. And then on the product side, we have conjugate base, and the H3O plus is the conjugate acid. So it could ask you which thing is acting as a stronger base. Is it the water or is it the acetate? Well, because the Ka value is so small, right, it's less than 1, it's going to greatly favor the reactants. So that means I'm going to have more of this and this present compared with the products. Bases, the stronger they are, will steal more hydrogens from the solution. So, because this reaction is very much reactants favored, the acetate is our stronger base, because most of the acetate is going to steal hydrogens from hydronium to form acetic acid again. So acetate is acting as a stronger base than water. So that's how you would compare those. Okay. They could give you a reaction or a solution with multiple acids and bases and ask you kind of the same thing, although that is more rare. But they could ask you the same thing about the acid. So if this is the acid, this is a base, this is a conjugate acid there. It's still, the Ka for HF is still less than 1, so it's still definitely reactant favored. So now, which acid is the stronger acid? Is it HF or is it H3O plus? Well, in terms of acid strength, the stronger the acid, the more it wants to give away its hydrogens. Okay, so H3O plus is acting as a stronger acid because it's reactant favored, so most of them are going to exist as HF. So H3O plus is a stronger acid than the HF. So just use your rules of equilibrium and make sure that you remember that the stronger acids, the more they want to give up their hydrogen, and the stronger base, the more they want to accept or pull in a hydrogen. They could ask you to compare the strengths of acids or bases based on Coulombic attractions, although this one is a little bit more rare. Let's look at something like H3N versus H3P. Those are both weak acids. Nitrogen has a smaller radius than phosphorus. Phosphorus has a larger radius. So because phosphorus has a larger radius, it has less of an attraction to the hydrogen ions. So this has less attraction, less Coulombic attraction. Because it has less attraction, the hydrogens leave easier. And because the hydrogens leave easier, that makes it more acidic. Remember, stronger acids want to lose their hydrogens. And the reverse is true for nitrogen. Nitrogen has stronger attractions, so the hydrogens don't leave as easy, making it a weaker acid. And so that's how you would explain using Coulomb's attractions. A more common question is they could ask you about the strength of the acid based on electronegativity, which typically comes up with oxyacids, so when there's oxygen present in the acid. Now these two, this is HOCl and HOClO. Most of the time we'll write this as HClO and HClO2. This is written this way to show the structure there. It's a little hard to see, but the hydrogen ions are here, sticking off the end of the oxygen. Now, the more oxygen atoms are in the oxyacid, the stronger the acid. So, more oxygens equals stronger acid. But that's not enough of an explanation for the AP exam. You need to know that because you have more oxygens present, there's more atoms that have a higher electronegativity. Oxygen has a pretty high electronegativity. And that means it's going to attract the electrons from the molecule closer to it. Because the electrons are not near the hydrogen, it makes the hydrogens easier to leave. So, the red parts in this kind of heat map of electrons. So this is more negative. The red parts are more negative. The blue parts are more positive. Again, because the electrons are on different parts of the molecule, it's going to allow the hydrogen, which is more positive, to leave. And the more the electrons are pulled away from the hydrogen, the easier it is for the hydrogen to leave. So that's what you need to say in your response. The same would be true for other atoms besides oxygen. It could be like a fluorine and chlorine. Anything that has a higher electronegativity is going to pull electrons away from the hydrogen and make it easier for the hydrogen to dissociate. Just really quick to review, carboxylic acids and nitrogenous bases. So these are organic acids and bases. Organic acids always have the structure COOH, which will have a C double bond O, OH, like this. And it could be attached to any other carbons. It could just be a hydrogen there. It could be other things. It doesn't, it doesn't really matter. But this hydrogen will act as the acid or the acidic hydrogen. Sometimes you'll see it written, acetic acid is kind of like this. So acetic acid just has a CH3 group there. So sometimes you'll see acetic acid written HC2H3O2. But sometimes you'll see it written as CH3COOH. And this one shows the structure, and it shows you that it's that carboxylic acid. But you could also have something called an amino acid. Now, an amino acid will have that COOH, but it will also have an amine group. Amine groups have nitrogen, and we'll have that lone pair on the nitrogen and at least two hydrogens, or at most two hydrogens. It could be attached to other things, but that amine group could act as a base because it has that lone pair. It can attract hydrogens to it to become NH3+. So amino acids are special because they can act as both an acid and a base. And I didn't fill in the extra spaces on this middle carbon because that's what makes the different amino acids different. They have different side chains, so that what differentiates between the different amino acids. And amino acids are used to make up proteins in our body. Another one that you might recognize from biology are the nitrogenous bases. So nitrogenous bases tend to have their ring structures. So they will either have 2 rings or 3 rings. Let me draw just one of them for you. Let's draw cytosine. This is cytosine C. So it will have a ring structure like this, and we'll have some double bonds, double bond O, like this, and then we've got some hydrogens. This has an NH2 group, just like that. Okay, so we have a lone pair on that nitrogen, a lone pair on this nitrogen, a lone pair on this nitrogen. So we've got some places here where the nitrogenous bases can actually act as a base. All right. So those are another example that just might pop up. You don't need to memorize them or anything. Same thing with the amino acids. You don't need to memorize that. Just be able to like recognize that these are examples of acids and bases in biology. So here are some examples, what kinds of questions you'll see about this. So how do you account for the difference in the pKa of acetic acid versus fluoroacetic acid? You could draw these out. They're both organic acids, they're carboxylic acids, but you don't really need to. So the biggest difference here is that you have 3 hydrogens on acetic acid versus 2 hydrogens and a fluorine on fluoroacetic acid. Anytime you see fluorine, you should think, ooh, electronegativity, because that's what makes fluorine so special. So because fluorine has a larger electronegativity, it's drawing the electrons away from the hydrogen. So electrons are going away from the hydrogen. This makes this hydrogen easier to leave, which makes it more acidic. That's why it has a lower pKa. It makes it more acidic. I will even say that again, because the fluorine has such a high electronegativity, it pulls the electrons away from the hydrogen, which makes it easier for the hydrogen to leave the compound, which makes it act as a stronger acid. Okay, so we have nitrous acid in this example. It's a weak acid, HNO2. In the water, it will form NO2 minus and H3O plus, and they give you its pKa value and Ka value. While nitric acid, HNO3, is a strong acid. Explain why nitric acid dissociates more completely than nitrous acid. So this is the same exact thing as our previous example. The biggest difference here is the difference between the 2 oxygens and the 3 oxygens. HNO3 has more oxygens present, so there's a greater electronegativity, pulling electrons away from the hydrogen, making it easier for the hydrogen to leave. So please make sure that you're able to explain based on electronegativity differences.